All right, little take-home physics for you. This will be all about finding our center. So 2 meter sticks. Balance one of those suckers right at the 50 centimeter mark. That should make sense. That is obviously the center of a meter stick. So for whatever reason, the planet Earth seems to prefer to tug on the 50 centimeter mark, right? And let's see if, ooh, I missed. So if we can flip this sucker here and get her to catch, ooh, darn it, we'll get there, we'll get there. Then what we're, ooh, nailed it, nailed it. Then you guys know if I were to try to balance it at say the 70 or at the 40, it would tilt, and it means the planet Earth, for whatever reason, does discriminate in this type of situation because it only cares about this object's center mass and center gravity, which for the most part are the same thing. There's a couple of instances where they wouldn't be. We'll learn about those a little later on. So what we were talking about is right now objects. They certainly have a center mass, which is what I was just referring to. And then if there are multiple objects having a multiple or having a common center mass, then this is the way you calculate it. What we'll do is, let's say there's two items, M1 and M2. And those two guys, then we're going to find out what their center mass is between the two of them. M1 happens to be 5 kgs and is at a 3-meter mark from where we decided to call 0. Fine. M2 is 8 kilograms, happens to be at the 9-meter mark away from where we called 0. So fine. What you do then is what I showed you in that previous video there, the introductory video. It is to get the center mass, just add up the products of their masses times their distances from the 0, divide by the sum of the masses. So in this example, it's really pretty simple. It'll be 5 times 3. So there's your mx plus the other mx, 8 times 9. Divided by the sum of their two masses put together, 6.7. So that one's not too bad. Now, what we'll also do then is say, well, gosh, what if we don't call that the 0 mark? What if that ain't nothing? What if nothing becomes right here? What if we say I want to start counting from the M1? Their center mass, physical location won't change, but the numerical way we communicate it will, because now we're referencing it from M1. And remember that M1 is at the 3-meter mark, so if that's the case, then my guess is it'll probably be 3 meters less than 6.7. So what we'll end up doing is say, okay, this sucker was initially at a 3-meter mark. M2 was initially called a 9-meter mark. So if we now call that 0, then this is at the 6-meter mark. So that's where that comes from. So M1 is still M1. X1, however, now becomes 0. So that whole term goes away, plus M2 X2 divided by, again, the mass whole. So we have 0 plus 8 times 6. But you still divide it by the same mass whole because it's the same two objects. And so there's the 3.7. It's 3 less than what it used to be, all right? And now what they'll also do is say, well, what if we have a system of items that are all interconnected and we can get one center mass for all of them? And that example would be something like this. They're going to talk about rods a lot, so say hi, Rod. Hi, Rod. In this case, there are 3 rods. So hello, Rod, and other rod, and other rod. And they will say they're uniform. What that means is their density doesn't change. It's the same composition anywhere you go along rods, and they're all made of the same material. So those 3 rods, same density. That's going to be key. So if this rod is L1, or is just called L, whatever length it is, it doesn't matter. Call it L. Then its mass is probably just going to be M. And if this rod here is 2L, then its mass is probably going to be 2m. And if this rod here is 3L, well then gosh, that one's probably going to be a mass of 3m. So what we're going to do is figure out what both an x and y center mass is for this system of 3 uniform rods. All right. First thing to realize, again, is to remind you what I showed you with those meter sticks. If this is a nice uniform rod, whatever, its center mass is in its geometric center. So this is at a height of L over 2. This is at a location along an axis of just plain old L. This is at a location on an axis that is 2L away, but it's lower on a y-axis from what we call our origin. So if this is L and this is 3L, well, then I'm thinking its center mass is 1.5 L, which means it's a half an L lower than what we called our 0 mark on a y-axis. So what we're going to do is we're going to break these down into x's and y's and just add up the m's and l's from the 0 mark. All right. First of all, on an axis, again, that center mass right there is 0 meters away from where we called the origin. On an axis, it's directly above it, so it's 0 meters away on an axis. So its mass, there's its m, there's its x. To that, I'm going to add the mass of the horizontal rod, which is 2m, and the distance its center is away on an axis from this 0 mark on an axis is just 1L away, because that rod was 2L, so its center is 1L. Then what we can do is take that other rod, it's 3L, which means its mass is 3m. And on an axis, at least, see how this rod is 2L, and that means from an x standpoint, that center mass is 2L away from what we call the origin. So then you have those, you will divide it by the mass of the whole system, which is m, plus 2m, which is the horizontal rod, plus 3m, which is the other vertical rod. You'll notice all the m's die. That 0 goes away anyway. And since the m's are gone, all you're doing is really adding 2 plus 3 times 2. So there's 6 plus 2 is 8. And then you're dividing that by 2m plus 3m plus m. That's 6. So it's 8 divided by 6. And we're calling that 4/3. The L stays right there with it. The M's die, but the L's don't. So from an X standpoint, the center mass of this particular system is 4/3 of a length away. So somewhere over there-ish is the X center mass of that system. Now for the Y center mass, all right, just to get the Y, where is it centered on a Y? This again is our 0 mark. If that's our 0 mark, then we will go up a half an L to get to that center mass. So on a y-axis, this is half an L away. On a y-axis, that X is a full L away. And what we said earlier, if this is the center of that one on a y-axis, it's half of an L below the 0 mark, because this is 1L. This is going to be 1.5 L's because it's the center of a 3L rod. So that half an L is below our 0. So that should end up giving us a negative 0.5 L, which there's the first rod, M. Its Y center mass is half a length above it. There's the horizontal rod, 2M. Its center mass on a y-axis is 1L above our 0. This longer vertical rod, again, its mass is 3m, and its center again is half an L below. That's why that 0, or that's why that negative is there. It's below the 0 mark. Divided by the same mass hole, because it's the same 3 rods, and you end up with a Y center mass that is 1/6 of an L above what we called the 0 mark. So That's where that dot comes from. So right there, that center is the center of all of that mass on both an X and a Y. That is the only place the planet Earth cares about that system of rods, all right? And so some practice questions to do with this. We have chapter 8 from the blue book, and don't tell me you never went to the library to get a blue book. Do numbers 10 and 11, and then you see something about a solar system, and that's what I'm going to explain to use right now. All right. Well, this setup should look familiar because it's what I just went over in terms of the question from the notes just now. Those are those 3 rods. These formulas should look familiar because that's what I did on the introductory video. And so what I'm going to do is say, let's pretend in our headsies that that's the sun, and in all of the planets, Mercury, Venus, Earth, all of them line up. Let's say let's pretend in our headsies they're all in a row. Mercury, Venus, Earth, there's Mars, and then Jupiter, that's a big one, and then Saturn, and then there's Uranus, Neptune, and if you want to put Pluto in there, by God, you go right ahead, huh? So let's just pretend in our headsies that all the planets are lined up just like that, which they're not, but hey, let's not let reality affect the physics, right? So you then can calculate the center mass of the entire solar system, provided it's lined up in this orientation. So what you would need to do is know the mass of the sun. You'd need to know the mass of Mercury, the mass of Venus, the mass of Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. So when you get all of those masses, then you'll also need to know how far away they are. So the centers are always what's communicated. So there's the X for Mercury. There's the X for Venus. There's the X for Earth. And so you'll have 9 or 10, including the sun, masses, and 9 distances. And what you will do is, again, just that, take the sum of the masses times their distances and divide it by the sum of the masses. And I want you to calculate the center mass of the solar system if the planets are all lined up just like that, okay? The center mass of the solar system. Once you get that number, then, just for comparison purposes, it'll be neat. I want you to divide that by the radius of the sun. And that will tell you if the center mass of the entire solar system is still inside the sun, or if it's a little outside the sun, or you'll compare it. How many sun radiuses away from the center of the sun is the center mass of the entire solar system? All right, it's a very interesting calculation. It'll take you a while, but hey, we got nothing but time, and with that, we have found our center. I will bring you a few more sample questions later on, but yay, physics.